Okay, am I audible to everyone? Okay, so I'll wait for 2 minutes for everyone to join and then I'll start the lecture. So my screen is also visible? Okay, fine. So let me start with today's lecture. So in the previous lecture, if you recall, we had finished discussing about one of the algorithm, that is bagging, sorry, not boosting. We had discussed about bagging and we had started the discussion about boosting algorithm in ensemble learning algorithms that we had studied. And why are we doing ensemble learning technique? Creating a classifier. Instead of creating a classifier with high variance, what we'll do, we'll combine multiple weak learners to create one strong learner. Okay. What was the idea behind this? If you recall, we had discussed one example also, that if we see that in case of movie review or movie recommendation, if you see, instead of getting a suggestion from any one person, you would consider the suggestion of multiple person as a base, right? If multiple persons suggest a particular movie, you might even watch it, right? So that is the main idea behind ensemble learning model, where we are combining multiple weak learners to create one strong learner. Okay, so in this case we had discussed about bagging technique. In bagging technique, which is known as bootstrap aggregation method, where we were performing we were creating random samples with replacement. If you recall, we were creating random samples with replacement from the given training data set, and we were passing into we were creating such multiple samples and we were passing it to multiple models. And in later on, these models, the output of these models were aggregated. That is, aggregated means, for example, if we are performing based on classification, if the model that is supposed to perform classification based task, then the aggregation will be maximum number of votes of a particular class that will be considered as your final classification result. And if the model is supposed to perform regression based task, then the output will be averaging of all the values. Okay, that is what the idea is behind aggregation. And one of the method of bagging we saw was random forest. in which we were considering the weak learners to be decision tree. The weak learners that we were using in this particular algorithm was decision tree, right? So far our discussion was up to this. Now our next discussion is about boosting algorithm. Okay, boosting algorithm, which is another type of ensemble learning method. And we had studied the basic idea behind boosting learning algorithm. So in bagging algorithm, what was happening is we were training the models parallelly. Yes or no? We were training the models parallelly. We were creating multiple samples of the training data set and we were training the model. And later on, we were aggregating this model. So parallel learning was there in the case of bagging, right? But in the case of boosting, what we'll try to do is we'll take one weak learner and boost it to become a strong learner. Okay, boost it to become a strong learning model. So how will we be performing is we won't be performing parallel learning in this. First, we'll take one weak learner. For example, we have a particular data set on which we'll be applying a weak learner. For example, here we are taking, for example, the decision tree stump we are taking as a weak learning model. Stump means what? Only one single node is there to perform the classification. That is known as decision tree stump. Okay, that is known as decision tree stump. That is only a single node to perform the classifications. For example, you have a data set where X and Y. So X is the feature. For example, X is the length of a particular length of a room, area of a room, and you are trying to predict price of that house, right? So what will be happening? We'll be dividing. For example, we'll be taking a particular splitting point. And we'll be dividing your data set into two halves. That is called decision tree stump, where only one single node is present to perform the classification or regression based task. That is known as decision tree stump, only one single node, right? So we'll be taking this particular decision tree stump to classify the data set. So first, it will perform the classification on your given data set, classification or regression based task on your given data set. Then what you will do, you will, for example, first, all the training samples, all the instances that are present in your data set, will have equal weights. All the instances will have equal weights. Later on, after first classification is performed, we'll identify that some of the samples, some of the instances are misclassified. So in the next classification, what we'll be performing is we'll increase the weight of those instances which were misclassified, and we'll pass it again into the classifier. So what will classifier do? It will try to classify. Bring to notice only those samples which were weakly classified. So it will try to classify correctly those samples which were misclassified in the previous classification, and it will again create another decision tree, boundary based on this particular now the weighted particular data set, right? So after performing the second classification, again we can find that certain data sets, certain instances are misclassified in this particular particular classification model that you created. So again we'll pass into another classifier by increasing the weight of only those samples which were misclassified and keeping the weight of another samples as it is. Or we'll be having a particular mathematical equation to change the weight. For example, we'll decrease the weight of those samples which were correctly classified and increase the weight of those samples which were incorrectly classified. So in short, what we'll do, the classifier will try to focus on only those samples which were misclassified in the previous classification model, and we will try to classify them correctly. So it is trying to improve the classification by at each point. Now, what we'll do in the final model, that, for example, we can perform for a particular weak classifier, we can perform 100 iterations. Okay, 100 iterations means 100 such classification models will be created, and later on we'll be combining with the SINUM function. We'll combine them all with the help of SINUM function, along with applying a weight matrix to all the classification that we have done, along with applying a weight to all the classification output that we have done. So in short, what will happen? This performance, weight means that is a performance associated with each classification model that we have generated. So for example, if the error for that particular classifier that we have generated is less, then the classification, that performance will be higher of that particular classifier. So in short, the classifier that gives good performance will be given higher weight in comparison to classifier which gives weak performance, and that output will be generating using sign-in function. Okay, the final output will be generated using sign-in function. So basic idea is clear to everyone? Yes, everyone is clear with the basic idea, yes or no? What will be happening in the case of boosting? Okay. What about others? Okay, yes, I'll repeat the last step of performance. So what will be happening is at each step of classification, that is at each step, for example, first iteration you have done, you have created a classifier, you have generated a classifier, and it is classifying a certain data point. Okay, it is generating a particular decision boundary based on it is generating a particular decision boundary. Now what you'll do, you'll estimate what is the performance of this particular classifier. Similarly, after end, you will estimate the error as well. So if the error of this particular classifier is less, then the performance will be higher, right? Similarly, after calculating the error, now you'll pass this particular data set, this weighted data set, to the next classifier, and again you will calculate the performance of this classifier and the error rate of this classifier. So what will do, the final classification will be aggregation of all the classifier that you have created, all the aggregation of all the, suppose 100 iteration you have done, so 100 classification models will be created. Okay, 100 classification models will be created, will be aggregation of this classification model, and will be applying a weight to all the outputs. So for example, if you have a particular test data set on which you have to identify whether it will be classified into class 1 or class 0. So what you'll do, you will calculate whether, for example, you are passing the data into the first model and you are getting certain prediction. For example, 1 is the prediction that you are getting. And along with that, you will apply a weight to that model. So weight is alpha. Here the performance matrix is the weight that you are applying to that model. So whichever model will have higher accuracy, whichever model will have good performance, that will be given higher importance as compared to that which is performing poorly. Yes or no? In the final aggregation, are you getting now what will be happening? And later on, we'll be applying sign-in function to get the output. Okay, I hope that is clear, right? So let us go through the algorithm once. I'll iterate through the algorithm once so that you will get the idea. Okay, I hope it is visible to everyone. Yes. Okay. Fine. So here, as you can see, this is the AdaBoost algorithm. We are currently studying the AdaBoost algorithm, in which what we are trying to do is, first what we'll be doing. First, we have a certain data set as shown in the figure. We have a certain data set that is present with you. And now we are we are taking a weak classifier to classify this particular data set. Okay, we'll be taking this weak classifier, and what we'll be doing, we'll be boosting this weak classifier to become a strong classifier at the end of AdaBoost algorithm. Right? That is what our idea is. So what is we doing is, first, all the training samples that are present with us, will be initializing them all with uniform weight. So basically the weight that will be assigning to all the samples will be 1 upon n, where n is the number of samples. Okay, number of samples that we have. So initially we'll be assigning a similar weight to all the training samples, and at time t, first time, what we'll be doing, we'll be passing this data into the classifier, and we'll be getting certain, based on this, what we'll do, we'll be getting certain classification error, right? So first what we'll do, the first step that we'll be performing is, we'll be passing this data into the classifier, and based on the classification that is being, based on the classification that will be performed by this particular model, we'll estimate what is the error and what is the performance of this particular model. And in this case, we'll be assigning a loss value as well with the data. So here we'll be using 0-1 loss function. 0-1 loss function in the case of AdaBoost. 0-1 loss means what? If the predicted value, h of x is the predicted value, is similar to the actual prediction. Okay, the predicted value is similar to the actual target value, then the loss will be equals to 0. And if the predicted value is not equals to the actual target value, then loss will be equals to 1. So this is known as 0-1 loss. Okay, this loss will be assigning to each of the training samples, and later on we'll be calculating the error rate of this particular classifier. Okay, what is the error rate that we'll be estimating is, we'll be summing the weight of all the misclassified data. Summing the weight of all the misclassified instances. Okay, that is what we'll be doing in the case of error. So this is the first step that we'll be doing is, first we'll be passing it to the classifier, then we'll be calculating the error. Let me come to the error part. Okay, so first we'll be training the model. H of t mentions the model that we have on the instances with the weight, initial weight that we'll be passing is 1 upon n. All the samples will be having 1 upon n weight. Then we'll be calculating the weighted error. The error will be the sum of weights of all the misclassified instances. So out of 10 instances, if we have 3 instances which are misclassified, the error will be the sum of all the weights of these 3 misclassified instances. That will be the error. Okay, fine. Next that we'll be doing is calculating the performance. The calculation of performance is 1 upon 2 log of natural log of 1 minus epsilon upon epsilon, which is here epsilon mentions the error that we have. Next step after this, after calculating the error in our classifier and the performance of our classifier, next step that we'll be doing is, we'll be increasing the weights of those samples which were misclassified, increasing the weight of those samples which are misclassified, and decreasing the weight of those samples which were correctly classified. Okay, so what is the formula for weight updation is, weight I plus 1 is equals to wi e raised to minus alpha, which alpha is the performance. Okay, here in the algorithm it is presented with beta, alpha into yi into h of x. So h of x is actually the predicted, yi is the actual label, this is a predicted label, this is the actual label, and alpha is the performance. Okay, so you can see, so suppose if yi is equals to, the actual label was -1, and if the predicted label was also -1, then the weight I plus 1 is equals to wi into e raised to minus alpha. Yes or no? So it will be decreasing the weight of correctly classified samples. Decreasing the weight, yes or no? The next weight of this sample will be decreasing. Similarly, if the y is equals to 1, the actual target value was 1, but the predicted target value was -1, then weight I plus 1 will be wi into e raised to alpha. So it will increase the weight. Okay, I hope this calculation is clear to everyone. So this is how we'll be increasing the weight of those samples which are misclassified and decreasing the weight of those samples which were correctly classified. So this calculation is clear to everyone, yes or no? Up to this, everyone is clear what we are trying to do? Okay, how we are decreasing the weight? Yes. See, so here I said that, for example, if the predicted actual target value is -1, actual target label is -1, and the predicted target label is also -1. Okay, predicted target label is also -1. So weight I plus 1 is equals to wi into e raised to minus alpha into y into h of x. Okay, so this is -1, this is also -1. So your weight I plus 1 equal to wi e raised to minus alpha. This is your new value, new weight for the next classification, new weight of the correctly classified instances for the next classification model in which you will be passing. So here you can see we are multiplying with e raised to minus alpha. So it will decrease the value, yes or no? But for misclassified samples, for example, if we have y label is equal to -1 and predicted value is equals to +1, So wi plus 1 is equals to wi e raised to minus alpha into y into h of x. So this both value will be opposite. The final will be wi plus 1 is equal to wi e raised to alpha. So it will increase the weight. Yes or no? Are you getting? It is multiplying with e raised to alpha. It will increase the value. Yes or no? Are you getting? What is step 5? Yes, step 5 is actually the performance. Here we are mentioning with beta, but it is actually the performance which I am mentioning as alpha, which is actually calculating the performance of the model that we are having, right? So this will be updating the weights of the model. Okay, up to this everyone is clear, right? We'll be updating the weight of all the instances that we have, and then similarly, now this updated weight, updated instances. So for example, we have 10 instances that we have. We'll update the weight of all the 10 instances for the next classifier in which we'll be passing. So in the next classifier, we'll be passing this updated weight. So the next classifier will focus more on those samples which are misclassified as compared to those samples which are correctly classified. So we'll again create a classification for the data set. For the data set that we are passing, again create a classification, that is for the decision tree stump. What is happening in the case of decision tree? It will create a line parallel to the axis. Okay, line parallel to the axis. This line is a parallel to y-axis, or it can create a line parallel to x-axis. This kind of decision in the case of 2D form, a decision boundary will be something like this. Okay. So it will classify again. It will classify again after performing the classification with second classifier. What we'll be doing is we'll again estimate the error and again estimate the performance of the model. Right? Again estimate the error, again estimate the performance of the model, and then we'll again update the weight and pass the data set into the next classification model, right? So in the end, what we'll be doing is we'll be combining all this classification model and we'll be applying a signing function to get the output, that the combined output. What is the combined output of the model? Okay, so for example, if all the models, for example, if we are passing a test data set and we are trying to predict whether it will fall into class 1 or class -1, that will be estimating using sign-in function. So you already know what is the sign-in function value. So if the value will be less than 0, the output will be -1, and value will be greater than 0, the output will be +1, right? I hope that is clear to everyone, sign-in function. Yes or no? Okay, Priyank has a doubt. Next classification model is same as, no, see, yes, classification, see, what we are doing is we are using the same classification model. That is, we are using the decision tree stump only to perform the classification, okay? We are, in the each classification, what we are using decision tree stump to perform the classification. The next classification will be using an updated training data set. That is what we'll be doing. We'll be using an updating training data set, which will have weight, the weight associated with each of the training data set. In previous decision tree, in the previous classifier, in the first classifier, all the training data set will have same weight. But in the next classifier, all the training samples will have updated weight. That is what we are doing. And this weight we'll be updating based on the error and the performance, right? So for example, for those samples which are correctly classified, the weight will be decreased, and those samples for which which are incorrectly classified, the weight will be increased, and then we'll be passing it into the model in the decision tree stump to perform the classification, so that the more focus will be given to those data which is misclassified in comparison to those correctly classified. Is it clear to everyone now? Okay, up to this everyone is clear? Yes or no? Okay, so this is your data. Yes, just a minute. The correctly classified data will be misclassified in the second iteration. Okay, right. Dave, good question. So there is a possibility. Dave has a question that, for example, in the first classifier, for example, we have a training data set like this, and suppose the correctly suppose in this particular data set, some of the samples are correctly classified. Okay, some of the samples are correctly classified, and in the second one, the same sample, for example, this was correctly classified, but this is misclassified in the next sample. But what we are doing, if you recall, in the final is what we are doing is we are using a sign-in function. Along with that, we are adding a performance metrics to all the output of the classification model. Okay, we are adding a performance. For example, if this model was giving an accuracy, it was giving a performance of 0.89, and the next classification model is giving a performance of 0.5, suppose, just consider, I'm just giving an example, then it's possible that what is the output, the more weight will be given to the output of the classifier which is giving good performance as compared to those classifier which is giving a little bit not better performance, right? So in the final classification, this will not impact much. Final classification, what will happen, we are not eliminating these models, the models that we have created, the sub models, the subset models that we have created, the that we are not eliminating, we are considering all the models when we are doing the final classification, right? When we are doing the final classification, final aggregation, we are considering all the models. That's why it is possible that the model will be performing better, will have higher weightage in comparison to those which are not performing much better, right? So in that case, this will be eliminated, this will be overshadowed in the final model that you are creating. Are you getting my point, Dave? What I'm trying to say here? Yes or no? Okay. And about the point that will this process will go on infinitely or stop this process after some point? Yes, that is a possibility that this model can also overfit. If you can see that this model can also overfit, if there is an outlier, if there is an outlier in this case, what will happen? It will keep on assigning this. What will happen? For example, it will perform the first classification and it will divide the data set and it will create a classification, right? It will create a classification for the first classification, then it will again perform certain classification. But for example, there is an outlier, it will constantly keep on increasing the weight of this particular data. Yes or no? Because it is not getting classified correctly, it will keep on increasing the weight of this particular data. Yes or no? Till a long time, for a long time, it will keep on increasing the weight of this particular data because it is not getting classified correctly. So we have to bring certain points in the consideration when we are performing this particular AdaBoost algorithm. One of the point that we have to consider is some of the algorithms, what they do is they assign a maximum weight. For example, the sample maximum weight should be 10. It should not go beyond 10 to perform a classification. So it will not increase the weight of that particular outlier beyond that. Also, we can keep the number of iteration. We can assign a number of iteration that we want to perform. So for example, we cannot perform infinitely many iteration. After a particular point of time, it will not do much better update to our training data set. So we can assign that up to 10 iteration, we want to, up to 10 different classifiers we want to create. And the final classification will be sign-up function of all those classifiers. Are you getting my point? Yes or no? Yes, Dave? Is the point clear now? Okay. So what should be the ideal value of T? Yes, okay. The ideal value of T, we cannot see most of these values, whenever we have an hyperparameter, the value of these hyperparameters we can easily identify using cross validation. Okay, is one of the techniques through which we can identify the value of this hyperparameter. For example, in the decision tree classifier also, we have certain hyperparameters. For example, if you recall, in the cost complexity pruning, we have certain alpha. Do not confuse this alpha with that alpha. So these all parameters we can estimate using cross validation. So you already know what is cross validation, right? Cross validation is that is a method to identify this hyperparameter value, where we'll be taking out a particular data set, we'll be separating the part of a particular data set as a part of validation, separating a part of the data set as a part of validation, and we'll be constantly checking that whether which value of T gives an optimal result, right? Are you getting my point? So in practical implementation, theoretically, I am just telling you that cross-validation is one of the methods. So whenever we are doing a practical implementation of this in Python, we'll get a more better idea. So these all hyperparameter values can be estimated using cross-validation, right? Are you getting? Okay. Anybody has any more questions? Okay, so up to this, everyone is clear, right? So this finishes our discussion on so our discussion on decision tree ends here. So what we have discussed so far in the case of decision tree is we discussed all the attribute selection methods in the case of decision tree, attribute selection methods, and based on that we also discussed some of the algorithms, right? Such as Gini index is one of the method, information gain, and similarly gain ratio. Okay, these are the methods that we discussed in the case of attribute selection method. Later on, we also discussed the pruning methods. Pruning methods to perform the pruning on the decision tree to eliminate the overfitting problem. Overfitting problem that we were facing in the case of decision tree. So pruning of the tree. So we had true pruning, post pruning, and pre-pruning. Okay, a pre-pruning and post-pruning method. And different cases in both of this, if you recall properly. In the case of post pruning, we also saw practically the cost complexity pruning. Okay, and we also practically saw the implementation of cost complexity pruning. Later on, after this, we studied about ensemble learning techniques and why we are utilizing ensemble learning techniques. What is the idea behind utilizing the ensemble learning techniques that we studied, and we saw some of the ensemble methods to aggregate. We also saw that diversity is very important in the case of ensemble learning techniques, because we want so the idea behind ensemble learning is combining multiple weak learners to create one strong learner. That is the main idea behind ensemble learning method. So this idea can be executed using diversity by enabling diversity in your different classifiers. Okay, so ensemble learning techniques, we studied two main techniques. It is bagging and boosting. Okay, two of the main techniques we studied is bagging and boosting, right? These are the two main important examples that we studied. So now suppose in this particular boosting example itself, suppose if I give you an example. So for example, I have a training data set and I have a prediction. Okay, there is a prediction I have. So I have a training data set X in which the actual label is 1, 1 and minus 1. And the predicted label is minus 1, 1 and minus 1. Okay, so can you tell me what will be the error in this case? What will be the error, and what will be the initial weight that will be assigning to all the samples? What will be the initial weight? Just I want to check whether you have understood this point or not. So what will be the initial weight that will be assigned to all the training samples? What will be the initial weight? Right now I am talking about AdaBoost technique, AdaBoost. So what will be the initial weight in of all the training samples? Yes, 1 by 3, right. 1 by 3 will be the initial weight of all the training samples. Since we have 3 training samples, so 1 by 3 will be the initial weight that will be assigning to all the training samples. Now, what will be the error? What will be the error? So we saw that error will be the sum of all the weights of all the misclassified data set. Sum of all the weights of all the misclassified data set. So which are the misclassified data set in this particular example that I have given? So what will be the error rate? Prince, I think 1 by 3 is right. Yes, I think you were trying to say 1 by 3 only, right? Yes. Okay. Yes, Keval is saying 2 by 3. So here, how many are misclassified? So here, these are the actual predictions. So first one is misclassified. So weight of that 1 by 3 plus the second. Okay, only one is misclassified if you see. So the weight will be 1 by 3. Yes or no? Rest of all is correctly classified. Yes. So weight will be 1 by 3, Keval. Okay. All right, so up to this, everyone is clear, right? Then what will be estimating? We have the error and we have the weight. So we'll be estimating the updated weight. So updated weight I plus 1 will be weight into alpha, e raised to minus alpha y into h of x, which is actual target value and the estimated target value. That is the predicted value. So for the first example, it will be 1 by 3 e raised to minus alpha. So first we have to estimate alpha, which is 1 by 2 ln 1 minus epsilon upon epsilon. This is natural log. So what we'll be doing? Log of 1 minus epsilon upon log 2. No, sorry. Yes, I think. No, log 2. In this case, I don't think we require, right? I think that is fine. We need not do log 2, right? So just check this once. Okay, everyone is clear with this? Yes or no? What we have to do in this calculation, if anybody is having any doubt in the calculation part? Okay, yes, log E, right? Yes. So it will do well, right? That won't be. I don't think that will. That is requirement of any division in this. Yes or no, Kevin? Okay, right. Fine. So everyone is clear with the calculation? Yes or no? Just let me know if everyone is clear with the calculation or not. How they have to perform the calculation. Okay. Okay. Yes, you have to perform the weight updation for all the training samples. So weight of correctly classified samples will be decreased, and weight of incorrectly classified samples will be increased. Okay. So you have to update the weight for all the training samples. Yes. Okay. So this ends our discussion on ensemble learning techniques. So now, after this ensemble learning techniques, we are starting our another topic, which is logistic regression. So if a certain topic is remaining, if I'll check again, if any of the topic is remaining for discussion, we'll discuss continue that in the next lecture. But right now we are starting with another topic. Sorry, just a minute. Okay, so right now we are starting. Just a minute. So now, after this, the first classification model we have discussed already, which is decision tree. Now we are starting with another classification model, which is logistic regression. Okay. Okay, I think my system is uh, hanging a little. Just a minute. Wait for 2 minutes. Okay. Um, I hope my screen is visible now. Yes or no? Is the screen visible? Okay, fine. So sorry for the inconvenience. Let us start. Okay, so we are going to discuss another of the classification method, which is called logistic regression. So this is another classification method that we have. In this, the main idea that we have, the main assumption that we'll be making is, so this is a classification algorithm. So what we'll be trying to do, we'll be dividing our data into the classification, into binary classification. First, we'll be talking about binary classification. In this case, in the case of logistic regression, we'll be talking about binary classification exclusively at this point of time. Later on, in the later discussion, we'll talk about multi-class classification and softmax regression. Okay, that we'll discuss later on. So for now, we'll suffice our discussion to binary classification, which will be yes or no class or cat or dog. These are all binary classification based problems. Okay, classifying in yes or no, or whether the animal is a dog or cat. All these are binary classification problem. So one of the assumptions that we make in the case of logistic regression algorithm is our data is linearly separable. Okay, our data is linearly separable. What do I mean by data is linearly separable means? For example, I have two classes. This 0 class is yes class, and I have X as no class. Okay, this is yes class and this is no class. So what do I mean by linearly separable? That I can draw a line such that it separates both of these classes. Okay, I can draw a line between these two data sets so that it will separate these two data sets easily. This is called linearly separable data. So what is non-linearly separable data will be something like this. For example, if you have a data set like this, for example, your data set is something like this, XXX, and your data is something like this. So here, if you can see, you cannot linearly separate this data. Yes or no? You cannot linearly separate this data. The linear separability is not present in this particular data set. So one of the assumptions in logistic regression is logistic regression will work well only when your data is linearly separable. So if your data is spread something like this, then your linearly separate, then this data set is linearly separable, and logistic regression will work well in these cases. First point is clear to everyone? Yes or no? This idea is clear? Okay, this is a classification model, Priyank. Yes, we have a, so in this, you might get confused with the name actually, because the name actually has logistic regression in this particular, but eliminate this particular idea because it is called logistic regression, but it is a classification algorithm. Okay, because of the name, you might get confused, but it is a classification algorithm. Okay. So first idea is clear to everyone that in this case, we'll be having a data which will be linearly separable. Okay, so the main idea, the main thing that logistic regression will perform is, what will logistic regression algorithm will try to do is, it will try to draw a line. So in case of decision tree, if you recall, what we are trying to do, the decision tree was actually drawing a line parallel to the axis to divide your data set. Yes or no? That is what decision tree geometrically does. Geometrically, what it does is it draws line to separate your data set parallel to axis. So if you have 2-dimensional data, it will draw a line which is parallel to axis. When you have 3-dimensional data, what it will do? It will draw a plane which separates the data set, right? So in the case of logistic regression, when we have 2-dimensional data set, what will it will try to do? It will try to draw a line which best fits your data, means tries to separate your data set properly. Okay, linearly separates your data set. That is what it is trying to do. The main idea behind logistic regression is this: it is trying to draw a line that linearly separates your both the data set. Okay, so here we are talking about binary classification. So only 2 classes are present at this point of time, which is, for example, X class and circle class. Okay, that is the 2 points that we have. So now let us start with the first discussion, that is discussion on the hypothesis representation, right? Okay, so one suppose we try to solve this particular problem using regression. Okay, try to solve this particular problem using simple linear regression. Simple linear regression. Let us use a simple linear regression. Simple linear regression is hypothesis h of x is equals to theta 0 plus theta 1 x plus theta 2 x2 and so on. Okay, simple linear regression. For example, in this particular training, for example, the data set that I'm considering as of now, training data set that I'm considering as of now contains two features x1 and x2, and we are trying to estimate y. So your hypothesis function will be something like this. Yes or no? Your hypothesis function will be something like this for simple linear regression. Yes or no? Yes? This will be your hypothesis function. So now what we'll be trying to do is, suppose we apply a regression algorithm. Suppose we apply a simple linear regression algorithm to divide a data. For example, your data set is something like this, so x, and here we have certain points here. And suppose I am using a linear regression to fit this particular data. What will happen? This will be certain, for example, this is a boundary that I'm creating. This is the boundary that I'm creating. Sorry, let us keep like this. This is a circle. Okay, so this is the decision tree that I'm this is the line that I'm creating to separate this particular data. Yes, but this is, if you see this value h of x will be very high. It will be much greater than 1 and 0. Suppose you have an outlier here. Suppose you have an outlier here. Now it will try to create another line here, and it will try to say that all the values on the right side of this particular line will be considered as positive, and all the values will be considered as negative for the rest of the on the left side of this particular line will be considered as negative. But if you see this classification that it is generating, it is not correct. Okay, this is not correct, and the values that it is generating is very high from 1 and 0. It is very high value it is generating, and based on these values, so h of x is equals to theta 0 plus theta 1 x plus theta 2 x2. And what we are trying to create is, for example, this value, this hypothesis value is having a value greater than 0.5. We'll estimate that all the values will be falling in the class 1, and if this value is having less than 0.5, we are creating a threshold value, then all the values will be classified as negative. But we can see that h of x in this case will not be from 0 to 1. It will be very high from 0 to 1. Yes or no? This value will be very high from 0 1. So we cannot consider this particular threshold to divide our data set. Are you getting the point? Are you getting what I'm trying to explain? Yes, this value will be very high from 1. Yes or no? Yes. What about others? Is everyone getting the point? What I'm trying to say here? Okay. Yes. So let me repeat. Yes. Okay. We need to fit h of x. Yes. Keval. I am coming to that point. Yes. I am coming to that point. So okay, I'll repeat this particular point so that we get to for those who are not getting this. So what we are trying to do is, for example, we have the main idea behind logistic regression. For example, you consider a threshold that if h of x is greater than 0.5, I'll estimate that the class that it is belonging, the data is belonging is 1. And if h of x is less than 0.5, I'll estimate that the class that it is belonging is 0. Okay, that is the assumption that you're making. But what will happen in this case is h of x value will not be between 0 and 1. It will be very high from 0 and 1. It will be very greater than 1. Yes or no? So this threshold value will not give you an approximately good estimate. So we cannot apply this threshold value here. So instead of this, what we are doing is we'll squash the value. That is, we'll try to reduce this value between 0 and 1. And for doing that, we'll be using a sigmoid function. Okay. In order to do that, we'll be using a sigmoid function. So what is sigmoid function formula? Sigmoid function formula is 1 upon e raised to minus x. Okay. This is a sigmoid function formula, and the graph of sigmoid function is something like this. Okay. So if we can, I may not be drawing this correctly. So value is between 0 and 1. if you see the sigmoid function value is between 0 and 1. And so what will happen if h of x, so what we'll be doing is we'll be applying a sigmoid function on this h of x. So our g of x will be a sigmoid of h of x. So we'll be squashing the value of our hypothesis between 0 and 1. Are you getting what I'm trying to say here? So, yes. No, actually not the difference. If you see, Priyank, we are not particularly talking about the difference. But what we are doing is, suppose in order to solve this logistic regression problem, suppose we utilize a simple linear regression algorithm. Suppose we utilize a simple linear regression problem, that is h of x is equals to theta 0 plus theta 1 x1 plus theta 2 x2. And then based on the value that I'm getting, I suppose keep a threshold that if h of x value is greater than 0.5, I'll estimate the classification is 1. And if h of x value is less than 0.5, I'll estimate the class is 0. Okay, this is a threshold value. Based on the threshold value, I'm assigning a class label. But what will happen if we apply a simple linear regression algorithm? The value of h of x will not be between 0 and 1 to estimate this, to keep this threshold value. That is what I'm trying to say here. So we cannot use this hypothesis function, that is a simple linear regression hypothesis function, to do the estimate in the case of logistic regression. Okay, to do the estimate in the case of logistic regression. That is why what we'll be doing is we'll be squashing. That is, we'll be reducing the value, hypothesis value, between 0 and 1, so that we can use this particular threshold to classify the data between as class 0 or class 1. Are you getting the point? Is this clear now? Yes, I'll repeat the sigmoid function once. Okay. Okay, so if you see, what is the sigmoid function formula is 1 upon 1 plus e raised to minus x. And if you see, the graph of sigmoid function is something like this. Yes, this is the graph of sigmoid function. And if you recall, this is 1 and this is 0. So if the value of x, suppose consider for random value of x, if value of x reaches infinity, what will be the value of sigmoid? Sigmoid will reach to 1. And if value of x reaches to minus infinity, the sigmoid will reach to 0. Yes or no? Put these values here and check by yourself. If you can check, if you e raised to minus infinity, for infinity, e raised to minus infinity, so it will be something like upon 1 plus e raised to infinity. Yes, so this value will be close to 1. And for rest of the values, this if x reaches to negative infinity, this value will be close to 0. Yes or no? So in short, the h of x. So our new hypothesis in the case of logistic regression will be squashing the value of hypothesis using the same hypothesis of linear regression, but squashing this between 0 and 1. That is applying a sigmoid function to this. Okay, so our hypothesis will be something like this. So this will be our hypothesis h of x. So our g of x is equals to sigmoid of h of x. So you can say that your hypothesis will be 1 upon 1 plus e raised to minus theta 0 plus theta 1 x1 plus theta 2 x2. In short, in the case of matrix representation, if you want to say in the case of matrix representation, it will be 1 plus e raised to minus theta transpose x. Are you getting? Is it clear now? Okay. So this will be your hypothesis function in the case of logistic regression. In the case of logistic regression, this will be your hypothesis function. So it will measure the value between 0 and 1, and you can keep a threshold value, 0.5. So if the value, what is the idea? How to read this particular, what is the intuition behind the h of x value that you are getting is, this can also be interpreted. This can also be interpreted as the probability of the instance belonging to class 1. Okay, the probability of the instance belonging to class 1. How it will be the probability of instance belonging to class 1 that I'm explaining. So for example, let us see. So suppose we have a data set like this. Okay. And the main idea is what? We are trying to create a decision boundary. We are trying to create a decision boundary which separates our two of the data set. Okay, this is what it is trying to do. This separates our both of the training data set. Now I am saying, what I'm saying is this h of x value that you are getting is probability, is actually a probability value that the data is belonging, that the instance is belonging to, probability of the instance belonging to class 1. Okay, instance belonging to class 1. That means what it is trying to do is, if you see theta 0 plus theta 1 x1 plus theta 2 x2, this is actually the distance of this particular point from this classification. And for all the points which are on this line, this distance will be equals to 0. So you can say, if you relate this with sigmoid function, you can say if sigmoid of x, whenever you are performing sigmoid of x, 1 upon e raised to minus x, if sigmoid x is equals to 0, sigmoid value is 0.5. If x is greater than 0, the sigmoid value reaches to 1, if it reaches to infinity. And if x reaches to minus infinity, the sigmoid value reaches to 0. Yes or no? So based on this, you can say that if the distance is greater than 0, based on this, you can say that this is actually estimating the probability that this particular instance is belonging to class 1. Suppose the h of x value is 0.001. So this is how much the probability of this belonging to class 1. So this will be higher probability. This will give you higher probability of it belonging to class 0. Yes or no? This point is clear to everyone? Up to this, everyone is clear? Yes or no? Any doubt? So I'll repeat this particular point in the next lecture. If it is not clear, I'll repeat this particular point. We'll continue from this point. But I suppose up to linear separability and sigmoid function, everyone is clear. Yes? Up to linear separability and sigmoid function, everyone is clear with the idea. Yes or no? So I'll repeat this probability thing from the next lecture. I'll continue from that in the next lecture so that you'll get better idea. Up to this, everyone is clear what logistic regression is doing and what is sigmoid function. How did we reach to sigmoid function? Okay. So fine. I'll stop the lecture here, and we'll continue with this discussion in the next lecture. Continue with the discussion of logistic regression from the next lecture. Right. So I am ending the lecture now.